Okay, so I'm writing a diagramming tool, and I need a way to route around different objects in the diagram. Of course, you can have different algorithms for different types of lines. This is what we're talking about here, is just preferring angled lines, 90-degree angled lines around objects. So in order to debug some of the issues I'm having, I decided to create this little program to give me a visualization of what's happening with the algorithm, and to be able to tweak things even on the fly while it's running. So I can set a begin and an end point, and it can be as simple as that. I can select either an A star or my hopped up A star, which I call dynamic, and I can select to show the route lines and explore lines. I can show the details as well. I'll leave that off for now. So by default, this is more or less just an A star using Manhattan heuristics, which is proximity heuristics. And it's, if you're familiar with how that works, it's basically, for the most part, it's just measuring step costs. So you can see it explored an area. It's quite large, but it did give me the right angle I'm looking for, which this dynamic routing does. But I can improve that by providing costs for leaving the end axis, leaving the begin axis, or even just leaving a straight line. So if I increase the cost of those steps, you'll see something happen. So it's now not exploring as much area, and if this was like this whole grid, the whole center would be empty, and it would just scoot around the outer sides. In fact, I can show that just by clicking like that. So that's greatly improved, but it still needs a little bit to be desired. But I can also add in obstacles. So let's say I add in obstacles like this, and again, this is just for testing purposes. And I can put lines on as well and have costs for trying to cut across lines. But let's put these back down again to 0, 0, and 0. So we're going to be at the default. We'll take a begin point. We'll put a begin point right here. Again, it's gone back to searching a large area. Change the end point, and we'll start playing around with the end point. So this looks fine. When I start playing it, it's not too bad. Small test. If I start playing out here, I can see that it's searching a lot of area to get into this position here. So then again, you'll see how this works. I can say for leaving the x-axis, leaving the y-axis, and breaking line. This will reduce it. Now that's a pretty drastic improvement. It basically beelined it straight for there. So that's great. And so on. If I took away the cost to break straight line, by the way, this thing will act differently. So now it's curving down like that. If I do a break line cost, it should, see, it took away one of the elbows because of the preference for keeping that straight line. And so this can be really quite powerful. I can set departure preferences for, or actually mandatory departure areas. So for example, I could want the endpoint to arrive from the south. And so it's changed the whole strategy to get into the south, which basically means I'm making an offset of one cell, the target, and then joining up the little bit of line that's left over. And I can do lines. So if I put a line across here, it's going to do the same right now, but if I start increasing the cost for the line, and you can see now it's avoided this line and gone down this way. So it's a pretty straightforward concept. You're adding cost to certain decisions that the pathfinding is making, and you're applying it to the step costs for the most part. I can see details in this particular one to show me what those costs are, the actual numbers. If you're familiar with A-star, you'll recognize the F, G, and H conventions. So now I can apply these settings over here inside my diagramming tool when I call up for a route, and I'll know, okay, this is the behavior I want, and I'll put these costs in.